Section 18.8 Equations. Before we can discuss the next topic, quantum simulated annealing, we need to discuss equations. Many ciphers can be expressed as a system of equations. The Balasso cipher can be expressed as C equals P plus K, where C is the ciphertext, P is the plaintext, and K is the key, all expressed as integers modulo 26. The Hill cipher is a set of linear equations. Ciphers like the Playfair and 2-square would be expressed as equations in base 5. Section 18.8.1 Transpositions. Transpositions are easily expressed as sets of equalities. For example, the columnar transposition can be expressed as C1 equals M1, C2 equals M4, C3 equals M7, C4 equals M2, C5 equals M5, C6 equals M3, C7 equals M6, where the MI are the plaintext message characters and the CJ are the ciphertext characters. Logical functions can be converted to numerical equations like this. Section 18.8.2 Substitutions. Substitutions can be converted to equation form by a three-step process. First, express each ciphertext bit as a Boolean expression using the bits of the key and the plaintext. For example, consider this substitution that takes a 1-bit key K and a 2-bit plaintext AB to produce a 2-bit ciphertext XY. Here, K bar, A bar, B bar means that K equals 0, A equals 0, and B equals 0. K bar, A bar, B means that K equals 0, A equals 0, and B equals 1, and so forth. The ciphertext bit X can now be written as X equals K bar, A bar, B plus K, A bar, B bar plus K, A, B bar plus KAB. There is a similar expression for Y. Section 18.8.3 Carnot maps. Carnot maps are used to reduce or simplify these expressions. This is the second step. The concept was invented by Maurice Carnot of Bell Labs in 1953. The idea is to picture the set of all possible n-bit inputs as an n-dimensional space, 2 times 2 times 2, and so on. Fill each cell where the output bit is 1. This is the space for the output bit X. There would be a similar map for Y. Notice how the columns in this map are labelled. As you move from one cell to the next, going left to right, only 1 bit changes at each step, including the wraparound step from column 4 to column 1. This arrangement is called a Gray code. Gray codes were invented by Frank Gray of Bell Labs in 1947. It is easy to construct a Gray code by appending 1 bit at a time. For example, to extend this 2-bit Gray code to a 3-bit Gray code, first you list the 4 AB pairs in the order A bar B bar, A B bar, AB, A bar B, with a C bar appended to each pair. Then you list them in the reverse order with a C appended to each pair. The C bit changes only twice, after the 4th code group and after the 8th code group, wrapping around to the start. The Carnot maps let you optimize the logic by eye up to about 6 bits, 3 horizontal and 3 vertical, which uses an 8-cell by 8-cell map. Above 6 bits, it is best to do it by a program. At each step, you add the largest rectangular block that fits within the filled region, and that covers at least one new cell that has not already been covered. Every dimension of the block must be a power of 2, so its volume will also be a power of 2. If there are several blocks of maximal size, choose the one that covers the most cells not yet covered. Continue until all filled cells are covered. In the KAB example, there are two 1x2 blocks in the filled region, namely KA and KB bar. Each one covers 2 cells. Since together they cover 3 cells, both are needed. That leaves only the cell KAB bar to be covered. So the reduced expression for X is KA plus KB bar plus KAB bar. The third step in expressing the substitution as a set of equations is to replace the and, or, and not functions in these expressions by arithmetic expressions, following the earlier rules. Section 18.8.4 Intermediate variables. If you attempt to express each ciphertext bit in a complex block cipher like AES as a single expression, the size of that expression will grow exponentially with each round. This problem is sometimes cited as a reason why you cannot use equations to break block ciphers. Horse feathers! This problem can be eliminated by using intermediate variables. Let the outputs of each round be a separate set of variables. The inputs to the first round, the key, the plaintext, and the chain vector, are independent variables. Any one of these bits may change independently of the others. The outputs of each round, or each stage within a round, are dependent variables. This includes the chain vectors for the next block. Their values are completely determined by the values of the independent variables. It is impossible to change one of these bits without changing some of the other variables. Section 18.8.5 Known plaintext. Suppose Emily has a quantity of known plaintext. For simplicity, let's suppose this is an n-bit message block. Her goal is to use the known plaintext and the intercepted ciphertext to determine the key. Suppose Emily has found an expression for each ciphertext bit in terms of the plaintext, the key, and possibly the chain vector. Let the expression for bit I be EI, and let CI be bit I of the ciphertext. For any given key K, Emily can measure the difference between the ciphertext that would result from enciphering the known plaintext using the key K and the intercepted ciphertext by calculating. When the correct key has been found, D of K will be 0. Here, D of K is called the objective function, or simply the score.